and open and unfit. So we've been working on classification so far, and let's just think of a really simple picture where we have some pluses out here, some minuses down here, but the boundary is not going to be perfect. You know, there's some pluses coming out this way, there's some minuses out here. And we are trying to figure out how we're going to draw our boundary between these objects, between these pluses and minuses. And let's suppose we're doing something like logistic regression. So logistic regression gives us maybe this is the p equals 0.5 boundary. So if we were going to cut off, so we're going to have this, basically there's going to be like this sigmoid that goes kind of along this diagonal that says, you know, definitely a plus, and down here is definitely minus. And then we have this probability, this curve over here. So this is maybe the 0.5. But there's other choices, right? So this could be the line corresponding to p equals 0.8. Maybe there's another line here corresponding to p equals 0.9. And then on this side, you know, probability of it being positive maybe is going down. So here's maybe a picture of what this might look like once you actually fit your classifier. And then we have a choice, right? We are, like, as designers of the system, we do not have to pick p equals 0.5, for example, to be our decision boundary. And in fact, if we decide, let me color these differently. So let me make these pluses red so they're easier to separate out. So if we have these red pluses, there might be situations where when the alert goes off, it's really important that the alert be correct, right? And so we might decide on this decision boundary over here, which is going to select these guys. So it's going to make mistakes on a bunch of points, but the ones we pick are definitely going to be bad, or, you know, the pluses. And there may be other situations when we say that, hey, it's really important to capture all of the pluses, even if we have some minuses mixed in. And so we might pick this region over here, right? We might pick the p equals 0.1 as our boundary instead. And that it helps us ensure that we catch all the positives, even though there's going to be some mess, there's going to be some negatives mixed in. So cases that try to include everything are cases that technically are called, you know, having high recall, because we're catching everything. Cases where we are pure, the things that we catch are pure. This would be high precision. And there's other metrics as well, but these are two important terms. One thing I'm also going to mention is different areas use different terms. So you might see precision and recall, you might see sensitivity and specificity. For me, it's always helpful to go back to the actual equations and see what they're actually measuring. But these are things that come up. I'm curious, like, you know, David, in some of your work or some of your examples, you know, where this comes up, where you're making decisions, and sometimes your decisions don't want a p equals 0.5.
Yeah, one example I like of this finale is I was at a workshop run by Google for next generation recommender systems about a year ago now. And one of the things that you worry about in recommender systems is you get these problematic feedback loops where the worry you have is that the content that's popular with other people is the stuff that you recommend, and that you don't manage to explore new content. And so if you have a overly precise recommender, then your market can begin to break over time. If you think about a recommender system as making a market by making recommendations from the supply side to the demand side, if it's only recommending the stuff that it thinks you're really, really likely to like, then maybe the system doesn't manage to bring new, in Google's case, they're thinking about YouTube, new content producers into the market. So you might want to pull that decision boundary back towards a lower probability to let more things through. And then you can immediately see the tension, right? If you do too much of that, then the recommenders will begin to appear, the recommendations will begin to appear noisy to the users. So it's kind of a clear trade-off that they're facing.
Yeah, and actually, speaking of media content, I was looking at some news articles about automated copyright notices. And so that's a situation where, you know, if there's some media that's up and it's being tagged as, you know, being infringing on copyright, should it be automatically filtered? Instagram and other platforms automatically filter out content. And in this case, maybe you want to be actually at this end over here, where anything you filter you should be pretty sure that this is something you want to filter out, because you might be excluding people from the platform. You don't want to, you may decide that you are okay with a few copyright infringements as long as people who are not infringing copyright, you know, are not mistakenly picked up.
Exactly. And everybody here at the moment might just want to think for a moment about these two settings. So think about a COVID test and think about an antibody test. And think about, in the case of an antibody test, are you interested in a low P or a high P? And think about with a COVID-19 test, low P or high P. So I'll just pause for a second. I encourage you all to think. And hopefully you've concluded that you want your antibody test to be very precise. You don't want false positives there. So you want that one to have a higher P. And you're probably willing to tolerate more false positives in your COVID test. So you'll pull that threshold lower.
Exactly. Cool. All right. So that was just a, you know, side discussion that I think is just useful to be thinking about, especially in the context of classification that we've been doing for the past couple of lectures. And now let's switch over to model selection. So here is where we are. Let's start with where we are. So we've been filling out our cube, and we have actually done all of these segments. So we have done regression in a non-probabilistic way, in a probabilistic way. We have thought about classification or discrete outputs in a non-probabilistic way and a probabilistic way. So we've filled out basically one half of the cube. And the second half, actually, we will start in the second half of the semester. But before we go on from supervised learning and we leave this cube behind, we're going to have a series of 3 topics diving deeper into some of the things that have been starting to come up as we went through this first half of the cube. And now we want to go into more detail. So preview for the second half of the first half of the term. Today and next time, we're going to be talking about selecting models. After that, we're going to be talking about more expressive models. You know, like we introduced the cube all through linear methods for most part. We had basis regression, but everything was linear. And what if you want things to be more expressive than linear models? And then finally, we're going to be talking about different choices or some alternative choices of losses. Instead of, you know, your squared error, your hinge loss, we already seen a few. How can we get more sophisticated with our losses? So picking models, expressive models, losses, that's a preview for the rest of this half of the semester. And today we're going to start out with this question of selecting models. And to some extent, when it comes to selecting models, we already have some amount of dilemma, right? You've seen in your first homework where we had, so in our first homework, we had our sunspots versus Republicans, and in that in that homework we had different basis functions. Right. So we already had multiple models over here that we were picking from, that we had the different basis functions that we could have chosen from. And at that time, you just tried a couple of different ones and you made some plots, and we made some qualitative discussion about which ones seemed to look good, right? Which ones seemed to be fitting the trend in the data the best. And our goal today is to make some of those observations that you might have made in that homework 1, question 4, much more concrete and precise. Okay, so I think also in terms of 181, If there's like one set of concepts that you leave with, I think it should be the concepts from this lecture, because this really gets to generalization. When do models work and why do they fail? At least one set of key reasons why this happens. Cool. So let's start out with a picture. So let's suppose that we have some data points that look like this. And our goal, again, is to go from X to predicting Y. So there's a couple ways I could fit these data points. I could fit it with something that's probably far too simple, right? So I could fit it with a line that looks like this. And we can see from this that it looks too simple. And what we're going to find it, or one way we're going to describe its simplicity, is that it has a high bias, right? There's a pattern in this data set, and we're just not fitting this pattern, right? So this is an example of something that's too simple, and it has bias in various places. Now, an alternative would be to have a model that has a really high polynomial, and thus manages to go through every single dot in this data set, right? And so its fit is perfect. But as you might notice from the way I drew this, and I did this on purpose, if we had a new X, let's say I'm trying to predict for like X right here, my prediction is going to be way down here. And that does not seem to be fitting the overall trend in the data at all, right? So I'm getting a bad guess, even though I have a more sophisticated model. And my issue here is that it's too complex, and this is giving me high variance. We're going to make this precise, right? So, but for now, this should match your intuition from what you've seen in homework 1.4. Right, so both of these regimes have problems. If you fit a model that's too simple, you're going to end up with errors, right? So if I was trying to predict for this X over here, the green model predicts here, that's bad. But the blue model also has problems, right? It predicts right here, and that's also bad. So our goal is to try to find, over here, we want to find models that generalize well, right? Fitting on the data we have is not good enough. We want to be able to make predictions on data that we have not seen yet before. All right. So to do that, how can we get good generalization? So today we're going to split this into 3 parts. We're going to talk about some basic techniques, to select models that will generalize. Next, we're going to talk about why models fail to generalize. And this is going to have to do with this bias and this variance. And then finally, we're going to talk about ways to get around bias variance trade-offs. So 3 parts that we're going to talk about. The first is going to be very practical, and same with the last. And in the middle, we're going to go into some of the math to really understand, why if we don't know why the models fail to generalize, we don't know why the ways are beneficial, right? So we're going to build up to these ways once we understand the why. But before that, step 1, let's start out with just the basic techniques. Like, what can you do, right, when you are in this sort of situation over here and you have to pick a particular set of models? So let's start with that. So basic strategies for model selection. I'm just going to name 2 that are quite related to each other. But these will serve you well, right? So this is meant to be just kind of practical, what you should do when you're trying to choose between different models. So if you have your data set of these XY pairs, I'm going to draw it like this. And like each pair is like a bin over here. So like this is an XY. You know, I've just organized my data into a line here. Each box is a data point. So if I have this data set, rather than training on the whole data set, one thing I can do is I can split this data set into pieces. And I can say that I'm going to have a part of the data set to train on part of the data. And then I can hold out some of this for validation. Validate. I'm going to explain what each of these are in just a moment. And then I'm going to have a test split. And then there's, this is still all, you know, this is all the data I have. So when I say this is a test split or it's some test data, it's not new data, but what I'm doing is I'm saying that, well, if my goal is to generalize to new data, what I can do is keep part of my current data separate, and that can help me simulate what it might be like when I see new data, right? So instead of training on this whole thing and then being surprised when I get a new data point, I'm going to train on just part of my data, and then I'm going to be able to measure what happens when I see a new data point. And that will help me understand, you know, will my model generalize well, right? So I'm simulating the process of getting new data, even though I have a fixed data set. So now what are, so this part is kind of easy to understand. You know, this is where we fit the model. Fit models, actually, because our whole goal is model selection. Then what's the goal of the validation piece? So the validation set, we're going to evaluate each model on the validation set. And that will give us scores for every single model. And once we have those scores, we can see which model seems to be doing the best. You know, maybe the first basis is too simple, the line is too simple. Maybe there's a squiggly that's far too squiggly, and in the middle you have something that looks quite reasonable, and that's getting the best validation error. Now the final piece is that once you have done this, you know, now pretend that you need to tell your boss how well you think this model is going to do out in the real world. And for that, you're going to evaluate only the best or the chosen model. And why do we separate out the validation and the test set? This is a bit of a subtle point. So here we were looking at every single model. And so, and one model happened to win, right? Well, the fact that it won means that maybe there was some aspect of it getting lucky, right? Like maybe this validation set over here just happened to be a great validation set for that particular model. So now that we've chosen it, we want to test, we want to get its numerical performance on a fresh piece of data that that model hasn't seen before, that it hasn't, you know, had the advantage of winning on already. Now in practice, you can't always split up you don't always have the luxury of having enough data to split it this many ways. But this is the kind of the ideal, right, that I'm giving you right now. And actually, if you have less data, there's a much more commonly used approach in this setting, which is called cross-validation. So in the case of cross-validation, similar idea, or I'm going to draw it in a similar way. You know, here are all my data points. And now I'm going to split my data into groups. And what I'm going to do is I'm going to train on one set of groups. So let's say version 1, I will train on these guys, and then I will validate on these guys. So I have my training set, and then I have my validation error that I measure. And then I'm going to alternate. I'm going to swap out different groups. So I'm going to say, now I'm going to train all of my models on sets 1, 2, and 4. I'm going to validate on this middle set over here, and so on. So I'll train on these guys, and validate on this one, and I'll train. Sorry, I'll train on the last set, and I'll validate on the first group. And what this, and then for each model, I will use the average of these validation errors, or the sum of these validation errors, as my total error. So we're going to use the sum of all validation error on each model as its score of how good it is, of how well it generalizes. And the advantage of this is that every part of the data gets to be part of the validation set. And we get to use more data in general for training. So in this case, like 3/4 of the data could have been used for training. If I split it 5 ways, then 80% of the data could have been used for training. Whereas up here, as I want to make my validation sets larger, because if I have too few things in the validation, how can I be confident about the number that I get? Let's imagine the extreme case where the validation set only has one element. I happen to get the classification wrong. Well, what does that mean? Right? Like, unless I have enough points in my validation set, I can't evaluate. And so I want this thing to be big enough that I can train a model, but I need the validation set to be large. But there's a tension, because if the validation set is large, then the training set will be small. And maybe I'm not going to be able to train a really good model with limited data. And I see the question about, can you use a different training and validation set per model? So every model is going to be trained on the same data and validated on the same data. So that's going to be what put it on an even playing field. But we have some choices about how we set up the validation. Is there just one validation set like this, or are we doing cross-validation where we're repeatedly, so every model gets trained 3/4, and then we compute a validation on the last quarter. Then every model gets trained on quarters 1, 2, and 4, and gets tested on the middle piece on set 3, etc. So these are two ways of doing this, and the cross-validation allows you to take advantage of the fact that you can train on more proportion of the data set. So there's another question about, if you have these 4 cases, which model do you pick? So this is what I mean by we sum up all of the validation errors. So there's going to be some error. So basically, with cross-validation, every point in the data set will end up being a validation point once. These points are in the validation in here. When we get to this group being the validation, these points will be part of the validation. So we just sum all of those errors. So at the end of the day, after we do the cross-validation, we have an error per, and we can just add. And there's also this question about, are we worried about having a test set in cross-validation? So this is, so you could also keep out one part of your data separately over here that you never touch. So this is never touched all the way through. And that ends up being the final test error, if you wish. And I see one more question about each row giving a different model. So that's right. So if you do something like cross-validation, you are going to end up with different models per row. So once you decide which model to use, one commonly used technique is to train your final model on all the data. Because once you've picked a model, you want to give that model the most data that you can and go with that. Cool. All right, so I'm not going to say too much more about these. Specifically when it comes to cross-validation, there is various theory about the best ways to do it and what sort of what it means, etc. But I'm going to treat these for the moment as basically practical tools that you have in your toolbox when it comes to how do you select models. These are simple and practical things that that work well and have basis in what we want the models to do, which is to generalize. All right. So actually, I think this is it's a little early, but it's the right time, but as we're switching topics, to take a 2-minute break. So why don't we take a brief break? Anyone who has questions about this validation can ask their questions, and then we'll come back for the bias variance trade-off theory and derivation.
Can I ask a quick question?
Go for it.
So each row gives a different model. So by model, what do you mean? Like, because I thought we like had fixed the model, but we would just have different weights for each training set. So I'm not sure what you mean by model anymore.
So let's say, so each row will have a different model, meaning that, let's say I'm trying to train, y hat equals W transpose phi of X.
Mm-hmm. Okay, so you take different phi for each row?
So, right, so each row here, because there's different data, might end up with different W's. Because here, this phi of X's, the training set, are going to be these guys over here.
Mm-hmm.
And then the next time around, your phi of X's are going to be this set, and this final set over here.
Yes.
So
But so when you say then, so when you say then we found the best model, so the weights are fixed, right, for that model. So why do we retrain it? Won't we get new weights then?
So in each one of these rows over here, you will end up with a different solved value of this W. And then once you have y hat W transpose B. So now you have a different basis, right? You have two different models that you're choosing between. And then as you're choosing between these two models, you see that, this one over here, maybe this one has the lower error, right? Let's say that that's just how it comes out in terms of the validation. Then before going ahead to like your testing or your final output, you would take all of the data, because you have 4 versions in this example of W. You would take all of the data and train your final model with basis V2, because you want to give it as much data as possible. All right. Let's see. So any other quick questions before we jump in?
Yeah, I have a quick question about why you would not use cross-validation, given that it allows you to train on as much of the data as possible. Like, are there any reasons for like not using cross-validation?
So from a bit more theoretical perspective, each of these repetitions, they're not independent, because they reuse like parts of the data. So like this, the first cut is part of the first 3 elements. And so so each of these validation errors are not exactly independent, like when you add them up. So that's the theoretical reason why cross-validation can go wrong. In practice, it turns out that it works quite well. So this is a place where in practice, this is a very practical and useful technique. But from a theoretical perspective, there are some edges here that are maybe not completely satisfying because of this correlation that you have in the validation errors. All right, I'm going to go ahead and move on to this bias variance trade-off. So this was the second thing that we were going to talk about today, is that why do models fail to generalize? So that's our like second question. Okay, so as I was hinting at before, there's this notion, that either if you fit something too complicated, you have this like high variance model, and if you fit something too simple, you have this like high bias model. And our error, is probably somewhere in between, right? That we want this Goldilocks model that's, you know, not too complex and not too simple. And the intuitive picture here, if we're looking at the complexity of the model, and we're looking at the error, is that as the model gets more complex, it can model more and more fancy things. So the bias is going to go down. But then as the model gets more and more complex, it can do all sorts of crazy wiggly stuff. And so the error due to the variance is going to go up. And this gives us this bias-variance trade-off that we're going to derive mathematically. But we see over here that if we add the bias and the variance together, you know, there's kind of this sweet spot where there's not a lot of error due to bias, there's not a lot of error due to variance. So that's what we're going to be looking for in our models, that we want them to fit, but we don't want them to overfit. All right. So what we care about, so we care about the expectation over y minus this hat y. Let's suppose we're going to be in a squared error setting. Let's say that this is the thing that we care about, that we are interested in, you know, and this expectation is over all y's that we could draw here, you know, for some particular location x. Let me adjust my notation a little bit. Just to make this a little clearer. Okay, so we're going to take an expectation over the y given x. I'm going to use like y of x to mean the y that corresponds to a particular location x, and y hat of x to be like our guess for what it means at that location x. At least, and I'm going to drop those, but I want to be explicit right now to say that it's for some particular location x. And this thing over here is going to be a function of your data set D. So this is your F data set calligraphic D of X, right? And so there's going to also be some variation that comes from the choice of the data set. But for now, we're looking at the error that comes from, you know, we had the fixed data set and we learned some F, and we are looking at the error over all the possible Y's that might happen because there might be some noise in Y, and also error that might come from this F not being perfect. Okay, so that's where we're going to expand. So note, there exists some mean value y bar for y bar of x for y of x. So there's a question about what is y given x. So everything here is going to be at a particular location x. So you can think about, if I scroll back up a little bit, I'm looking at the error that's happening at one value of x. Because there's an expectation we could take over the entire data set, but I don't want to worry about that part right now. That's not going to be the relevant part for this derivation. So I'm always assuming for everything going forward that it's always going to be at one location x. All right. So we have some value y bar. So and this is normal, right? In the sense, or kind of to be expected, that the y's might be all over the place, but in the world there exists a mean value. Like if you sat at x and you collected values of y at that x for a long period of time, there's going to be a mean value of those numbers that you collect over time, right, as you just sit at one location x. So I'm going to incorporate that into this expression, and I'm going to say that this expression over here is equal to, you know, y given x, y of x minus y bar of x plus, sorry, I keep forgetting that front print, minus y hat of x squared, right? All I've done here is added and subtracted 0. So, or added a 0 by adding and subtracting. So that part is cool. And now I'm going to treat this thing as a term and this thing as a term as I FOIL out my squared. So this is going to give me an expectation y given x of 3 terms. We're going to have a y minus y bar squared. We're going to have a expectation of y bar minus y hat of x squared plus 2 y given x. So this is just me multiplying out the terms that I defined up above. Yeah. And now let's stare at these terms. So this over here is this is noise, right? This is irreducible noise, because I could have the best possible guess of y bar, and I'm still going to run into trouble because, like y is not always equal to y bar. Like every time I sit down and take a measurement, let's say I'm using well, thermometer is fairly reliable, but let's say I'm taking a measurement with like an IMU or some more fancy sensor. Every time I try to take a measurement, it's not going to give me exactly the right value. It's going to give me some noise around the correct value. And no matter how well I do with my fit, I'm not going to be able to fit that. Right. So this is one source of error that's just not going to go away. And now let's look at the second term over here. So this is the mean value. Let me actually, I think I'm seeing some of the questions. Let me expand this into a picture. So if I'm sitting here at a particular x, let's say this is y bar. This is the actual mean value that for the data, and the data are looking kind of like this, right? So they're distributed around their mean values. And so if I'm sitting here, I have some y bar. I might have measured this y out here. That y it has some error, and this error right here, that's the error, that's the noise. Now the second term, let's suppose this is my y hat of x. So I can't really be penalized for not fitting y, right? That was a hopeless effort. But I can be penalized for not fitting y bar, right? I should have been able to do that because that doesn't depend on the noise, right? This is a solvable problem. So this is error from the model. Right? So this is the part over here that I should be able to do, right? This is the part that I hope that I can fix or to learn. And then this last term over here, well, the y bar doesn't depend on the actual sampled value of y. Neither does y hat. So we are left. This is the only term over here that depends on the sampled value of y. Yes, in the second expression, this does depend on the data that's used to train. So this there should be like it depends on the specific data set. So we're going to tease apart the effect of the data sets in just a minute. We haven't taken any expectations over data sets yet. This is just seeing like for a specific data set, where would this where might our errors be coming from? Okay. And so, yeah, that's a useful point. So over here, we have y minus y bar. Well, kind of by definition, the expectation of y minus y bar is 0. So this whole term is going to be 0 over here. So that's a little key, especially I think I remember seeing it for the first time. It's like, okay, this term goes away. This term, the first term is noise, and the second one represents the error from our modeling. So this tells us what we can hope to do. So the second term is the term that we're going to look at now in a little bit more detail. Okay, so now let's try to think about this term actually, right. So let's clarify some of these expectations. So we have expectation of y given x of this y minus like y hat from a particular data set of x squared. Y bar. This doesn't depend on the y anymore, right? So we just have this term that's y bar minus y hat for this particular data set x squared. So that's going to be our issue, or that's going to be the error that comes up for a particular case, right? For a particular case, this is the error that's going to come up. And now I can ask the following question, how will this model error term behave over multiple tries, multiple data sets, right? Like what is that term gonna look like in expectation? Because this is fixed to a particular data set, but I'm curious about its behavior overall, right? Because I don't want to, or it's hard to think about any particular data set, but I want to understand what it's going to look like in general. If I were to sample data sets, is there going to be a lot of variation? What's it going to look like as I play around with these different terms? So now I'm going to introduce this additional expectation. Yep, Mark.
I think a few people still had a few questions about the terms above going to 0, but it may have gone out of the screen a little bit quickly.
Oh, okay, sure. Here we are.
Feel free to go ahead, but I was wondering if now is a good time for those people to ask a question or two about that.
Yeah, yeah, go for it. Yeah, thanks for flagging. You want to jump in?
I think there were just questions about why the last term goes to 0 again, and why doesn't the first term?
Oh, I see. Okay, so the first term has the squared right here. So the expectation of the error squared doesn't go to 0 because that's the variance. Over here, we have only one copy of y minus y bar. That's this first term over here. So that's this y minus y bar. And then it's being multiplied by a term that is y bar minus y hat. But not y bar does not depend on the noise in y, right? That's where this expectation is being taken. And y hat is just a number, right? Like given any x, y hat is a number. There's no noise in that either. So given x, it's just a number. So y bar minus y hat here is just a number. And so the only randomness that is in this second or this last term is coming from this y, this first y over here. And so the first term we have, and the first expression that we have is y minus y bar times a number. And so linearity of expectations, the y hat minus y bar, y bar minus y hat, the second term can just be pulled out. It doesn't matter, it's just a number. And then we have the expectation of y minus y bar, which by definition is 0.
So just to clarify for the questions in the chat, it doesn't so much have to do with model fit, but it's more that by definition, there is a term where we're just subtracting the two means from each other and they equal each other.
Exactly. Yes. Yes. Cool. Thanks for jumping in, and definitely please do that again in future. All right. So now let's see how this term over here, which is our model fit term or lack of model fit term, behaves over now multiple data sets. So now I want to know, what is this term going to look like if I'm going to start averaging over multiple attempts at trying to fit the data. Yes, and we're still all at 1 point. I'll try to remember to put in the x's. Good. Okay, so this term can be split up in a very similar fashion to, we're going to play the same sort of game, that if we had lots of different data sets, every time we get a data set, there is going to be a fit that we're going to get. And we can take the average of those fits, right? So there exists an average predicted value. And the average prediction now is over multiple data sets. Every time we get a data set, we get a new prediction, y hat. And if we averaged over all of those predictions, y hat, that gives us the mean prediction, y hat. Now averaging again over multiple data sets, over multiple fits. Yeah. So now we're thinking about every time we get a new data set, we fit a new y hat. And I'm going to switch over to writing this down. I'm going to switch notation to F just because it's going to be a little cleaner. So I'm going to say y bar of X minus F data set of X. So every time I fit, I'm going to get a different value. So I'm going to say we don't need a data set anymore. F bar of X be the expectation over data sets of our fit, right? So every time we get a data set, we fit a new line. And this is the average of all of those lines that we have. And again, it's going to be, I'm constructing this, and then we're going to see why it has value in just a few moments. So let's now play a very similar game to the game that we played before. We have y bar of X. This is the real mean, right? I want to emphasize that. That's the real mean of the data. Minus F bar plus F bar. So we're doing this. And this is the mean of my predictions, right? My predictions don't have to match the real mean, right? So again, really important distinction between y bar and F bar. Y bar is like reality, the real actual average value. And F bar is the average of my fits, which may or may not be perfect, will not be perfect in general. So here we go. And now we're going to do the same sort of thing that we did before to end up with expectation over data sets, y bar of X. Let me just write this out, and then I will talk through it. So I'm not trying to write and talk at the same time. All right, so now we have 3 terms, and these 3 terms come about in the same way that these 3 terms over here came out. I'm doing the same sort of thing, except playing the game with these F bars. So let's look at each of these terms. Well, the first term doesn't depend on the data set. It's just y bar minus F bar, so we can ignore this part over here. But this term is what we're going to call the bias squared. Because this error is coming, it's not because we had our data set, our data set just got unlucky, we got a bad fit. No, we took the average over all of the possible data sets, right? And that average value was still wrong. So think about this case where we're fitting, again, like the parabola. And let's say every time we try to fit the parabola with a line, here's one line that comes through, here's another line, here's another line. Depending on which particular set of points you draw on the parabola, you might get slightly different lines. This is, let's say, the mean line, again, for sake of example. So this one would be equivalent to F bar, and these are different F data sets. And that F bar is still bad, right? Here's the mean value. So here is Y bar. And here's F bar. And Y bar and F bar are not the same because your model was just not good enough, right? It wasn't that the data set was unlucky. It was your model was not good enough. So that's the situation where you have bias. Now, the next term over here is called the variance term. And the reason it's called the variance is that, hey, every time you get a different data set, maybe you just get a completely different fit to your model. And let's illustrate kind of what's happening there. So here's your data set. I'm fitting it with like my crazy curve that has to go through all the points. And now I choose let's say I draw a different data set in thicker circles. And because I have the capacity to fit this, maybe I'm going to fit another curve that's completely different. And I end up with completely different predictions. So in this case, maybe, F bar might have looked like this, but F data sets are all over the place. Yeah. So on any particular data set, I'm likely to do a bad job because my fit for that data set is totally wacky, right? Even though the mean value might have been quite good. So the bias might have been small, but the variance now is large. And then the final term is going to be 0 because this is a expectation over data sets that only appears in this term over here. So this ends up being a constant by the same sort of argument that I made for the first case. And now in the second term, F bar minus F data set, by definition, this expectation is 0. So what I end up with is that my error, there's some part that's noise, there's some part that's bias squared, and there's some part that's coming from variance. This is not in our control. And this is in our control. So let me pause there. This is like a really important point, and like probably, again, one of the most important points of the entire course in terms of understanding where these errors come from. So I love to take questions.
May I ask a question?
Go for it.
So this equation that you have here, we started with this expectation over all y given x, and you said that like this is what we were interested in, and then at some point we introduced the expectation over all data sets, and I'm just wondering when that happened. Like.
So that was when I was starting to analyze this second term. Actually, I could have done it from the beginning now that I think about it.
So where would that have been at the beginning?
So we could have said that we care about this expectation as well. Like we care about.
Okay, gotcha.
Error over possible data sets as well.
Okay.
I don't know what's clear for folks. If it's clear to think about both expectations being there from the beginning, or whether it's clearer to say, here's what happens, and now let's look at the expectation of this thing because we're not sure which data set we're going to get. It's a good point. Other folks?
I have a quick question. Like just you said that the bias comes from that our model is not good enough. So how is the variance comes from?
So the variance comes from the fact that I end up fitting, for any particular data set, I end up fitting a model that's quite far from its mean. So this squiggly example of, let's say I have a really high degree polynomial, and I'm trying to fit that really high degree polynomial, then wherever my points happen to land, and maybe actually too many points makes the example look more complicated. But let's say I just have 3 points and I'm trying to fit this with a high degree polynomial. I might end up with a fit that looks, like this. But if and let's say the true data, go like this. And then let's say I have another model, another set of points. So I resample the data set and I'm going to draw it with squares. So I end up with these particular 3 points in my data set this new time round. And this is even in a case where there's no noise. And I try to now fit another model. I might end up fitting a model that does this, right? Because if I'm fitting these cubics, then there's nothing, as long as they go through those points, there's nothing telling the model that, hey, you're doing a bad job. Like, hey, it's really silly to go down here. So it might be that if I average over all the different ways to fit this data, all of these fits, I do end up with the correct mean value. But any particular time I go about trying to fit this, fit these data, I'm going to end up with a model, the sample of the model that is quite far away from its mean value and quite, quite all over the place.
Could you go over once more when this D notation was brought in?
Yeah, so I think we have some choices as I think about it. I'm thinking about it as I'm doing this. So we could have done it from the very beginning. We could have said that we're interested in, as we go over all data sets, as we go over any noise, what is our error going to be? So I think maybe it's a little complicated to think about from the beginning, but maybe it's simpler because then you don't need to change your viewpoint mindset as I'm realizing this. So we can think about from the very beginning, there's two sources of variation. There's noise in the world, and then there's the data set that we were given. And we want to know what is our squared error over those two sources, noise in the world and the data set we were given. And then the whole thing can be just kind of follow through. Like I will leave this here. This becomes expectation. Like this. Alternatively, you can think of one piece at a time, and it's kind of up to you what's simpler. I think maybe now that I'm re-looking at it, I think maybe we should have just introduced the D's from the beginning and not said, let's analyze this term later. So let's try it this way. So there's two sources of error. There's the noise, and then there's the noise in the world, and then there's the noise of which particular data set you happen to get. Okay, so let me now very briefly, and so to make sure we have time for a concept check, go through the last part. So remember, I said we're going to have 3 parts today. We're going to talk about some basic strategies, which is cross-validation and validation. Then we were going to talk about this bias-variance trade-off, right? This very important trade-off between if you have two simple models. If you have two simple models, this is the too simple case. You end up with high bias. You just can't fit the data. If you have two complex models, then you're going to end up being very dependent, very sensitive to your data set. And because you're very sensitive to your data set, you're still going to end up with potentially really high errors. So the last part is like ways to mitigate this bias variance trade-off. And in particular, our goal is going to be having expressive models but we want to control the variance. Because if we don't have expressive models, we're screwed, right? If our models cannot express the function that we're trying to fit, then the bias is high and we're just stuck, right? There's nothing we can do about that. However, if we are in a situation where we have expressive models and then we are like, oh no, like when we have these really complicated expressive models, the variance is really high, it's very sensitive to the data. Now we have a knob that we're going to be able to tune a bit and try to say, how can we have those expressive models, but make sure that the variance is not too high, right? So that's the intuition. So I'm going to mention 2 different things, but the intuition is going to be the same or very similar, is that we want to have expressive models that control variance. So one technique is regularization. And when we, so regularization is this idea, let's say our parameters are W for the model. So we're trying to minimize W for some loss, right? Could have been your hinge loss, could have been your squared loss, could have been whatever loss. And now I'm going to add an additional penalty. For example, I might say that I want the W's to not be too large, right? So this is our penalty. This is the same thing as our regularization, right? That's what I mean by regularization. And what this particular penalty is doing is it's saying that don't let the W's be too large, right? So if I'm fitting a polynomial, then maybe cubic polynomials like this are okay, but I don't want one of these, right? I don't want polynomials that have really large values if I can avoid them, right? So this is a soft penalty. Rather than saying, hey, all cubics are great, it's saying that, well, cubics with low weights are great, right? If you can do it. If you can't do it, it's okay, but because we want an expressive model. But if you can fit a simpler model, by this definition of simple is like smaller weights, then fit a model with simpler weights if you can. Another common penalty is L1. And this is saying that, I'm giving you a cubic, but if you can set some of those to 0, that would be great. Fit it with a line, perfect. Fit it with just a parabola. Oh, that's great too, right? So this one wants, we'll prefer smaller weights overall. This will prefer sparse weights. And you can imagine in general, there's lots of functions that you could put in, just some regularizer of W that's going to limit the number of models that you have to, it's going to penalize the more complicated versions in that particular model class, right? So you don't have to give up on your model class. You don't have to say that, hey, I guess I'm just stuck with a line, can't fit that cubic. You can have your cubic, but you encourage your cubic to be simple in some way if possible. The other approach, which I'm just going to mention really briefly because I do want to make sure that we have time for a concept check, is this notion of ensembles. So this idea of averaging over multiple models. And I'm not going to go into, so the R of W is a regularizer. So you can choose whatever regularizer makes sense for your application. Here's 2 common ones, but there's lots that could make sense. So ensembles, you're averaging over multiple models. And there are many, many ways of building these ensembles. I'm just gonna, there's bagging, boosting, random forests, gradient boosted trees. There's a lot of different techniques out there. And a core idea here is that if you average over multiple models that are, let's say you do bootstraps of your data. So you take subsets of your data, you fit models to each subset of the data, and then you average over those, then you're getting rid of the variance while keeping the bias low, right? So by averaging over models, we're getting closer to that F bar rather than F data. So as long as F bar was good, as long as we had sufficiently expressive class when we put things together, then we can still do well on our prediction. So that's an intuition for ensembles and why ensembles can do well. Again, I'm not going to go into detail for those, but so this is, I think, super cool to me, at least. I don't know, I just find this cool because we just derived, why models go wrong. We said that the models are not expressive enough or they have too much variation, and now we have some fixes, right? We say make the models expressive, but try to control the variance in various ways. All right, so with that, now that we've had this introduction, let us switch over to a concept check. I'm gonna close this. I'm going to copy over the link and paste it into the chat. All right, and let me quickly screen share the actual concept check so you can take a look together. Here we go. All right. So here's the concept check. So the premise of this concept check is quite simple, but the intuition is quite deep and important. So we have two models, a model from model A, basically, and model B. And model A has a train accuracy of 0.9, but when you test it on a test data set, that accuracy drops to 0.6. So on new data, it drops to 0.6. Model B, on the other hand, when you train it, has a lower accuracy, 0.7, but when you try it on new data, it has a value of 0.7. Oh, sorry, 0.72, and then on new data, it's 0.7. So given only this information, we want to go through and ask, will adding additional training data perhaps help? That's something we didn't really talk about in this lecture, but it's something to think about. We'll come back and regroup about it. Would having a validation set, so early stopping could be like, is a technique to stop training early. If you're not familiar with that, don't worry about it, but think about it as like limiting the number of bases or number of coefficients. You can definitely reason about that. And then if you trained on a new data set, would you expect the classifications to be the same or different? So we're going to go ahead and send everyone to breakout rooms for about 3 minutes for you to brainstorm, and then we'll come back and regroup on these questions. All right, folks, I know that wasn't a ton of time, and I see that people are continuing to enter responses, which is fantastic. So I'm just going to briefly go through the arguments for these as we're short on time. So the first question was, as we add, for each model, will additional training data help? I'll share the responses coming in. So if we have, let's think about what additional training data does. So if we have lots of training data, there's less wiggle room. Intuitively, there's less wiggle room for the model. Think about the case of just even linear regression. If we have 1 point, high variance, right? There's all sorts of models that we could fit to that. If we have 2 points and only those 2 points with low noise, then the line is fixed. So that's an intuition that you can use. That if in that pictures that I was drawing with all the weird squiggles, if I have a degree polynomial of size 6, size 7, once I have 20, 30, 50, 100 data points, that model is going to become more and more fixed, even if it has a higher degree polynomial. So if we believe that the difference in train and test accuracy in class A is coming from, for model A, is coming from variance, right? Because train accuracy was great, right? It threaded its way through all the points, but the test accuracy just tanked. It was bad. So if the test accuracy was bad, again, it's probably because it's doing too many wiggles, and adding more data will help prevent those wiggles from happening, because it's going to pin down the model, right? The model has too many degrees of freedom. The more data you add, all of those degrees of freedom are getting pinned down. Whereas with model class B, it probably not going to help, because it kind of is where it is, right? It's already fit, and adding more data is probably not going to make a huge difference. For the second question, you can read this question as, would doing something fancy help? And a majority of the folks are saying yes. And so if the model is overfitting, it has high variance. We just talked about things that might help, like the regularization, ensembles, and these are other things. So yeah, it seems reasonable that doing something fancy might help. Again, model trained from class B, this is the model that's probably not the best fit for the data, and there's, doing something fancy to that, it's probably not going to help, because the issue is probably coming from bias. And so now you're told, if you expect that the model is underfitting, right, it has bias, it's too simple, If you got a new data set, it's still going to be too simple, right? It's not going to help with the predictions, and probably the line is going to be the same. So if you have those different parabolas, the line that's going to fit to those parabolas is kind of like the same line. Whereas with model class A, so class seems to be on the right track there. You know, that it's going to be about the same. So with the yeses. And then with model A, that's the one that was super wiggly because it was trying to go through, again, think in your head, trying to go through every single point. Don't care what I do in between, but I got to get through every single point. If you're given a new data set, now you have to play the game of going through every single point. You're probably going to make very different predictions on a new point. So this intuition about the no is exactly spot on. So there we go. This is our, plays through of bias versus variance, and I'm happy to stick around and answer a few questions after class.